Ions. The word ion has a general meaning that can be applied in a lot of different circumstances. Generally speaking, an ion is any chemical species that has a charge. The term species in this setting simply refers to any piece of matter, such as an atom, a molecule, or a compound. It's a general term chemists use when they don't want to commit to being more specific. An ion is a charged chemical species, so it could be an atom with a positive or negative charge, or it could be a compound with a positive or negative charge. Ions form because atoms are capable of gaining and losing electrons from their outermost shell. You'll remember from before, we talked about the idea that the electrons in an atom exist in a very particular arrangement or configuration around the outside of the atom's nucleus. That configuration isn't static. It's always moving, and those electrons can actually be lost or additional electrons can be gained by any given atom. We usually refer to these outermost electrons from the electron configuration as valence electrons. And you can always count the number of valence electrons in an atom by looking at its electron configuration and counting the electrons in the shell with the highest number. While that's practical, it's not always the most efficient thing to do because, as you remember, electron configurations can take a while to write out in all their detail. For this reason, it's useful to remember a shortcut. If you look at the group number that an atom is in on the periodic table, that group number is actually the same as the number of valence electrons in that particular atom. So for instance, if you choose an element from group 1, all of the elements in group 1 have exactly one valence electron. In other words, no matter how many electrons are in their configuration, only one is in the outermost shell. If you look at group 2, all of those elements have two valence electrons. Group 3 have three valence electrons, and so on. The transition metals are a little bit more complicated, so we won't really cover them in much detail in this course, but you can remember this shortcut for working with any of the elements in groups 1 through 8. To understand why ions exist, we have to talk about the stability of atoms. The most stable atoms on the periodic table are those atoms that don't react. The atoms that don't react, you may remember, are group 8, the noble gases. The noble gases are chemically inert. They don't react easily with other elements, and the reason for this is that they're very stable on their own. All of the other elements on the periodic table are less stable than the noble gases, and this is part of what makes them so interesting. One way that people think about the chemistry of the elements on the periodic table is to say that atoms on the periodic table want to be isoelectronic with these noble gases. Isoelectronic is a term that means having the same electron configuration. It comes from the term same, iso, and electronic, which stands for the electron configuration. Now, atoms don't have personalities, so when we use the term want, we're actually just implying that they're most stable. Other atoms on the periodic table are most stable when they have the same electron configuration as a noble gas. How can they get the same electron configuration as a noble gas? Well, since they don't have it to start with, they can either gain or lose electrons to accomplish this. This is often referred to as the octet rule. The reason for this is that the noble gases, with one exception, are in group 8, and so they have 8 valence electrons. This is called a perfect octet, and because we know atoms are the most stable when they have a perfect octet, we think of all the other elements on the periodic table as trying to get a perfect octet. There are some exceptions to this octet rule. We'll get into some of them later in this course, but the two to be very aware of are the elements that are in the first period of the periodic table. Those elements are hydrogen and helium. Hydrogen and helium don't follow the octet rule because they are such small atoms that they can't possibly have 8 valence electrons. For this reason, hydrogen and helium often are said to follow the duet rule, meaning that they only need 2 electrons to be as stable as a noble gas. That should make sense because if you look carefully at helium, atomic number 2 on your periodic table, it appears in the same column as the noble gases, group 8. However, it only has 2 valence electrons because it only has a first shell with an s subshell. Let's take a second to look at why an atom might become an ion so that it can have a perfect octet. Or in other words, why does gaining or losing an electron give it the ability to become isoelectronic with a noble gas? I'm going to use the example of sodium. If you find sodium on your periodic table, its atomic number is 11, meaning that it has 11 protons. As we know from our previous lectures, in order to be neutral, if it has 11 protons with positive charges, it must also have 11 electrons because they carry negative charges. So neutral sodium, or elemental sodium, has 11 protons and 11 electrons. Now let's think about the sodium's valence shell. The outermost shell on this sodium contains 1 valence electron. We could figure that out by writing the electron configuration for sodium and seeing that it ends with 3s1, 1 valence electron, or we could use the shortcut. Sodium's in group 1, so it has to have 1 valence electron. Sodium, as you already know, is not very stable in its elemental state. It's an alkali metal, so it's incredibly reactive with water. When sodium reacts, it reacts in such a way as to try to become isoelectronic with a noble gas. There's 2 ways it could become isoelectronic with a noble gas. If it has 1 valence electron, one way to get 8 valence electrons would be to gain 7 additional electrons. By gaining 7 additional electrons, sodium, at least theoretically, would have 8 valence electrons. This would mean the sodium still had 11 protons in its nucleus, but it now would have 18 electrons. Sodium with 18 electrons would be just like the noble gas that has 18 electrons. It would be isoelectronic with the gas argon. While theoretically that is a more stable state, it's really unlikely to happen in nature, and here's the reason why. Sodium, when it gains those 7 electrons, will have 7 more negative charges than the neutral sodium started with. We would write that as sodium with a superscript 7 and a negative charge. Sodium 7- would be a very unstable ion because all of those electrons would be repelling each other. Not to mention the fact that the sodium atom would need to find 7 electrons to steal off of other atoms or substances. So while theoretically this would work, it's very unlikely to happen in nature. Fortunately for sodium, there's another option. Instead of gaining 7 electrons, sodium also has the option of losing the 1 valence electron that it has in its outermost shell. When sodium loses 1 electron, it essentially strips off its outermost shell. And what's underneath that shell? Well, the complete second shell that was formed before that final valence electron was added to the sodium atom. In other words, this is very similar to how onions grow. If you have an onion that has some damage to its outermost layer, you could put it back in the ground and hope that it grows a whole new layer, kind of like when sodium theoretically gains 7 electrons. But in reality, what most of us will do is simply strip off the outermost layer to reveal a clean, full layer underneath. This is essentially the same idea behind what sodium does. Sodium gives up 1 electron, resulting in the fact that while it still has 11 protons, it now has just 10 electrons. Now it's isoelectronic with the noble gas that has 10 electrons, better known as neon. Furthermore, the sodium itself now has 11 positive charges and 10 negative charges. So we would write the symbol as sodium plus. You could write sodium plus 1 or sodium 1 plus, but sodium plus is more typical and is totally sufficient. This gets to the core of why and how ions form. By gaining or losing the outermost electrons of an atom, that atom can become isoelectronic with a noble gas. The consequence is that it has either a positive or negative charge. It's also convenient because, based on the number of valence electrons an atom starts with, it's very easy to predict which ion it'll form. Let's look at how. When atoms gain or lose electrons, they form what are referred to as cations or anions. Cations simply mean any atom that develops a positive charge. The sodium we just looked at is sodium +1, so we could refer to it as a sodium ion, or more specifically, the sodium cation. Anion refers to any atom that becomes an ion with a negative charge. So it could be -1, -2, -3, or something else. Based on the location on the periodic table, it's relatively easy to predict which elements form which cations and which anions. Any element that has 3 or fewer valence electrons generally will be more likely to lose those electrons in the same way that the sodium lost the electron to become isoelectronic with the noble gas that preceded it. Remember that the group number is the same as the number of valence electrons, so this includes group 1, group 2, and group 3 on the periodic table, as well as all of the transition metals. That means that all the elements in group 1 tend to form a 1 positive charge. Hydrogen forms the hydrogen ion, H+. Lithium forms the lithium ion, Li+. Sodium, as we saw, forms the sodium ion, Na+, and the pattern continues down the group. The elements in group 2 have 2 valence electrons, so they're likely to form a 2 positive charge. Beryllium forms Be2+, magnesium, Mg2+, calcium, Ca2+, and so on. Group 3, starting with boron, can form ions that have a 3 positive charge. And the transition metals also form positive charges, although it's difficult to predict which ones without having a larger chemistry background. So we know that the transition metals tend to be cations, but while they have positive charges, we don't know whether it's +1, +2, +3, etc., without more information. On the other side of the periodic table, the elements in group 5, 6, and 7 have 5 or more valence electrons, so they'll usually gain electrons. That means that the elements in group 5 tend to form a 3 negative charge. The reason for this is that an element like nitrogen needs to gain 3 electrons to become isoelectronic with neon, so it's likely to become N3-. Oxygen is likely to form a -2 charge, along with everything else in group 6. Group 7 is likely to form a -1 charge, because these elements only need to gain 1 electron to become isoelectronic with the gas directly to their right. There's 2 groups on the periodic table that I haven't numbered, and the reason for that is that group 4, carbon, silicon, and so on, rarely forms ions on its own. The reason is they're essentially stuck in the middle. They're darned if they do, darned if they don't, because they either have to gain or lose 4 electrons. Because that's not likely to happen, we often don't see these in their pure ionic form. The same thing is true for group 8, except that group 8 is our noble gases, so they don't need to gain or lose electrons because they already are noble gases. They're already very stable. When it comes to talking about the different ions, naming them is fairly straightforward, although there's a little bit of added detail with particular ions that you should be aware of. Anytime you're working with a cation, because it's easy to predict what charge that ion is likely to have, we don't often give the charge itself, we just give the name of the element and if necessary add the word ion on the end. For instance, I mentioned that lithium, in group 1, tends to form lithium +1. We rarely refer to it as this, however. We simply call it the lithium ion. Now you try. Mg2+. What should we call this? Well, if you find Mg on your periodic table, it's number 12, magnesium. and it's in group 2, which is why it forms a 2 positive charge. Because that's easy to figure out, we likely will just call it the magnesium ion. We won't call it magnesium 2+, because it's a little redundant. This isn't true when you're working with transition metals, because transition metals can vary in which charges they have, and in fact one element can actually form ions with several different charges. We're required to give the charge of the ion along with the name. That charge will always be positive, so we give the number usually in terms of Roman numerals. If you have trouble remembering your Roman numerals, you don't have to remember very high for this. Just remember that the number 1 looks like an I, the number 2 looks like 2 I's joined together, as does the number 3 look like 3 I's. The number 4 is a V preceded by an I, meaning V, which is 5, minus 1. 5 would be just a V, and that's about as far as you'll see for most of this class. So for example, iron, which is a transition metal, it has atomic number 26, would be a positive charge, but we wouldn't know what its charge was if we didn't have any more information. So in this case, if we're talking about iron 3+, it would be referred to as the iron 3 ion. And in writing, we'd write iron with the Roman numeral 3 in parentheses. Now you try. Figure out what Zn2+ would be called. Remember, you can pause the video if you want. Zn, just for a hint, is number 30 on your periodic table. If you found number 30 on your periodic table, you know that Zn stands for zinc. And as a transition metal, we don't know what its charge is if it wasn't given. Here, however, I called it Zn2+. So to give it its name, I would call it zinc 2, or the zinc 2 ion. And if I want to write it, I would write it using a Roman numeral. This takes care of naming cations as well as the cations formed by transition metals. There's a slightly different rule when it comes to naming anions, and that's that you take the name of the element, but you change it to have an "ide" ending. And if you want, you can still use the word ion. In a lot of cases, these might sound awkward until you say them out loud, and then you're likely to recognize many of these ions. For example, F on the periodic table is atomic number 9, fluorine. Because fluorine's in group 7, we know that it'll form a -1 charge. But we don't call it the fluorine ion. Because it forms an anion, we call it the fluoride ion. Fluoride, just like the fluoride that can be found in toothpaste. Try naming this one. All right, you probably recognized O right away for being oxygen. Oxygen's in group 6, so it has a 2- charge, but when we name it, we need to give it an "ide" ending. Again, try saying it out loud and you're likely to figure out the correct way to say it. It's not oxygenide, it's simply oxide. We would call this the oxide ion. And in fact, most of the elements in group 7 and group 6 will sound familiar to you if you say them with the "ide" ending. Group 7 consists of fluorine, chlorine, bromine, and iodine, but if you say the names of the ions, you'll recognize fluoride, chloride, bromide, and iodide. Try it for group 6, and you might recognize some other common names as well. Even though many of the elements on the periodic table are more stable as ions than as elemental atoms, it doesn't mean that there's no cost to the process of gaining or losing electrons. In fact, when an atom does lose an electron, there's an energy cost to this process, meaning that you have to put some energy in to get the process to happen. The reason for this can be understood by remembering that protons in the nucleus of an atom are attracted to the electrons in the orbitals of the atom itself. Because the protons and electrons are attracted to each other, it's a little bit like the attraction that happens between a refrigerator and a refrigerator magnet. The protons and the electrons are attracted to each other, so to pull them apart requires putting in a little bit of energy. This is a lot like the energy that would be required to pull a magnet off of a refrigerator. This cost, or required amount of energy, is referred to as the ionization energy, essentially the energy required to form an ion. ionization energy refers specifically to the process of an atom losing an electron. And if you think about it, it's easy to predict which elements and which atoms on the periodic table have a high cost for losing electrons versus smaller costs. If you think about the periodic table, there are particular elements which are very close to becoming stable or isoelectronic with a noble gas if they gain an electron. For instance, let's compare the elements fluorine and lithium. Fluorine and lithium both can become ions. However, as we've seen, fluorine in group 7 only needs to gain one electron to be isoelectronic with the neon that it's next to. Lithium, on the other hand, needs to lose one electron to become isoelectronic with helium. Thinking about this fact, which of these elements do you think will require the greatest cost to lose electrons? In other words, which of these atoms is most excited to lose electrons? Well, lithium, if it loses one electron, will become isoelectronic with a noble gas, whereas fluorine, if it loses an electron, just gets further away from the noble gas. Because of this, lithium has a smaller cost of losing electrons or a smaller ionization energy. And in fact, fluorine is the element on the periodic table that's often referred to as having the highest ionization energy. The general trend on the periodic table is that the elements in the upper right-hand corner tend to have relatively high ionization energies. These are elements that do not want to lose electrons, because in fact they'd much rather gain them. The elements on the left side of the periodic table have a small cost for losing electrons. It's not hard to coax an electron away from them because they're more stable after the fact. The further down the periodic table you go, the smaller that cost gets, basically because the atoms become larger and larger. So an element like cesium or francium has a very small ionization energy, because as soon as it loses an electron, it becomes isoelectronic with a noble gas. Sometimes we talk about the cost of losing electrons, other times we talk about the benefit to gaining them. In either case, we're looking at the same concept. Measuring the benefit of gaining an electron, or the amount of energy you gain from allowing an atom and electron to come together, is what's referred to as electron affinity. And the trend is the same. Fluorine, while it's hardest to coax electrons away from, it's the one that gets the greatest benefit when it gains electrons. So fluorine has both the highest ionization energy and the highest electron affinity of most of the elements on the periodic table. There are exceptions to this rule. Most specifically, there's exceptions where you're dealing with two elements that are right next to each other on the periodic table. In cases where you compare elements that are very close to each other on the periodic table, you have to look at their electron configuration to determine which one would actually have the highest electron affinity or ionization energy. In cases where an atom has to lose an electron that's paired, that always has a higher energy cost or a higher ionization energy than if an element has to lose an unpaired electron. Even though that's relevant in some specific cases, I just want you to remember the general concept of ionization energy and electron affinity as it applies to elements broadly apart from each other on the periodic table.
All of the ions we've seen so far have consisted of a single atom that's either gained or lost electrons to become positively or negatively charged. There are, however, many ions out there that are made up of more than one single atom. These are called polyatomic ions. Polyatomic ions are any ion that's made of two or more atoms that have a charge. Let's look at a couple examples. One type of polyatomic ion is called cyanide. Cyanide has the chemical formula Cn-. Notice it has two different elements. It has a carbon atom and it also has a nitrogen atom. This carbon and nitrogen are bonded together through something called a covalent bond, which we'll be looking at in more detail. For now, the only thing we need to concern ourselves with is that that molecule of carbon and nitrogen bonded together has a 1- charge. So the entire thing has a 1- charge, and therefore we'll be treating it in chemical formulas the same way we would treat any other element or any other ion that has a 1- charge. Another example of a polyatomic ion is carbonate. Carbonate is more complex than cyanide. It's comprised of 1 carbon atom and 3 oxygen atoms. With those 3 oxygen atoms bonded covalently to the carbon, the entire molecule has one 2- charge. So it's a 2- charge, the way many other ions we've seen can have a 2- charge. What's important to realize about these polyatomic ions is even though they are more complex, in chemical formulas we'll be treating them the same way as any other ion.
Cyanide and carbonate are just 2 examples of polyatomic ions, but there's many, many more out there. Most textbooks, including yours, have a chart that lists common polyatomic ions in their names, chemical formulas, and charges. We've already discussed cyanide and carbonate, but you're likely to recognize the names of several, if not many, of these polyatomic ions. For instance, you might have heard of nitrate. Nitrate is a polyatomic ion that consists of 1 nitrogen and 3 oxygen atoms. It has a charge of -1. You may also have heard of phosphate, which has the chemical formula 1 phosphorus and 4 oxygen atoms with a 3- charge. The bicarbonate ion, HCO3-, is also very common and important in the health sciences. You're not required to memorize these polyatomic ions, but you'll probably start to recognize the names of many of them.